All right, so today we're looking at rotational kinetic energy, which is kind of a big topic with some of the longest equations that we've seen all year, probably the longest equations, but they're kind of fun to work as well. Anyway, we'll kind of introduce this topic and kind of relate it back to what we've looked at before. So previously we've looked at conservation of mechanical energy, where we give us something like this, give us an incline, and we had some kind of a block, and that block would slide down the incline, and we were able to say, all right, well, we had PE up top here, and that got transformed into KE down here at the bottom. And so we could set up a conservation equation that looked something like this. PE at the top of the hill equals KE at the bottom. And if we were solving something like velocity or height of the hill or things like that, it was pretty straightforward overall to set this up. And we'd have an equation that looked like that, and we could solve for, any of these variables that we wanted to. We also saw that mass would cancel out, and mass didn't affect the velocity of this thing down at the bottom of the ramp. So that's what we've kind of done in the past. That's going to compare to what we do now, because we're going to have the same kind of problem, so some kind of an incline. But now up at the top of the incline is something that's capable of rolling. And so once we introduce rolling, the game changes a little bit. It's still kind of the same basic idea. So we're still going to have PE up here at the top, and at the bottom we are going to have kinetic energy. The only change is that because this thing is rolling, we're now actually going to see the introduction of a different type of kinetic energy. So before, we had, I guess, no idea that there were multiple forms of kinetic energy. We've kind of saved that until this point. And so there's this traditional type of kinetic energy that gets called translational kinetic energy. Translational kinetic energy is the kinetic energy that we've talked about all year. So no changes there. It's still going to have that kinetic energy because it's moving when it gets down here to the bottom. The new form of kinetic energy that we have to talk about is this rotational kinetic energy. So this object, because it's capable of rolling, is actually going to have rotational kinetic energy as well as this translational kinetic energy as well. So maybe I'll write those out just so you can kind of see those. So we have translational KE, and then we have rotational KE. Rotational KE. So I always, in my mind, think of translational KE as traditional. So that is the run-of-the-mill, traditional, run-of-the-mill kinetic energy that we've discussed already. Rotational, yeah, that didn't look right. The rotational kinetic energy that's here, this is the new one. So this is the one we're going to kind of introduce. So that's the general idea. We'll get to an equation here in a second. One conceptual point that we need to talk about here is in order for this object to roll. So we've got this hoop or whatever this might be sitting at the top of this slope. In order for it to roll, there has to be friction. If this surface is frictional, which could be a nice little trick question to be hit with, if this surface is frictionless, then this object actually won't roll at all. It'll actually slide, which will actually make the problem easier to solve because it'll be exactly like this. We had this block here that slid down the incline. This ring would actually slide down the incline without rotating at all if there were no friction. So there has to be friction. In particular, what we're looking at for that to take place is static friction. So if you think about this thing kind of rotating, as it gets down here to the bottom, it's in contact, and the bottom isn't really moving until the next split second. And so it's that static friction right there that causes the thing actually to start to rotate. It kind of applies a torque on this and gets it to spin. So always think static friction, and if there is static friction, then your object will roll and not slide. So that's kind of big. Okay, enough with that. Let's look at the new equation. The new equation that we're looking at for this rotational KE, one that we haven't seen before, is going to look like this. So I always call this one, there's different ways to notate it. I like to go KE rot. That's just showing me that that's the KE, the rotational KE from this thing spinning. And it's going to look a lot similar, and it's adapted from the kinetic energy equation. Let's do that one kind of side by side. KE, we can put traditional down here. We don't need to. But that one we know for sure is 1/2 mv squared. And so we'll adapt that equation just like we have all the equations in this chapter. It's not just the mass, but where the mass is located at, which is our I value for rotational inertia. And then it's not a linear velocity. We are now looking at angular velocity instead. So from this equation that we've used a whole bunch, produces this, this rotational equivalent for kinetic energy. So I think maybe the best thing to do is kind of to jump into an example and actually work an example out with you here. That's kind of the run through. That's the new equation. That equation does show up on the AP sheet, so no need to memorize that one. Although I think it'll kind of stick with you a little bit since it's so similar. But yeah, let's look at, if we had a problem that looks something like this. Got a ring, and that ring is rolling down an inclined plane with a height of 3 meters, and it wants us to find the velocity of this thing at the bottom. So the drawing is going to look basically exactly like what we had on that previous piece of paper. Something like this. We do know that this height is 3 meters. Seems like not a lot of information, but let's just kind of jump in and try to figure this out. It wants the velocity, how fast this thing is moving once it gets down here to the bottom. And so we know for sure that we've got PE to start, and then we've got KE down here, but we got to remember that we've got two forms of kinetic energy and not just one. And so we got to work that into our equation here. So the way this is going to get set up is we've got PE at the beginning of our problem and KE at the end. This one wants it at the end of the problem. These would get dramatically more difficult if we stop something in the middle, where you would also still have PE as well. Dramatically is probably not the word. It would get more difficult. You'd have more to do. It would all be fine. But we'll start with one that looks like this. So we've got PE, and that's going to be regular KE plus our KE rot, KE rotational. So that's kind of the beginning of this, and we're going to see this expand way out with a whole bunch of variables, and then we're going to shrink it back down almost kind of in an amazing form, like how little information we're going to need. So I'm going to go ahead and start filling in some of this. All the things that we know. So we've got PE, which is mgh. We've got our kinetic energy equation from our energy chapter. And then this is the new part, KE rotational. So we've got our 1/2 I omega squared. Okay, so not much we can do from there. We're going to keep working on this. Remember, this is going to vary depending on, let me get the rest of the problem down there. This is going to vary depending on what the object is. And you notice up here it tells us it's a ring. And remember, rings have high rotational inertia. And so the equation here is going to be mass radius squared, or as we've come to name it, Mr. squared. So I'm going to plug that in next. So all of this first part stays the same, except now we're going to expand that I value up. Since it's a ring, there's Mr. squared. And we got that worked out. Now the nice thing about expanding that out is, if you notice, each part of the equation now has mass in there. And so that is how we can see right here, it doesn't really look like much is going to cancel out, but as soon as we expand that I out and we put Mr. squared, now you can actually see the masses cancel. So I'm going to rewrite this again. It actually simplified a little bit there. Down to that, just making sure I got everything filled in there right. I think I did. And then from here, you know, we kind of stop and it's like, well, all right, all that I know is that the height of this thing is 3 meters. And we look down here at our equation and we've got tons of variables left. There's our height, we know g, but we don't know anything about these velocities we're trying to solve for. We've got an angular velocity there, we've got a radius of the ring, we're still nowhere close. And so the trick with some of these is to say, all right, well, this right here, this angular velocity, could be written a different way, because think about the equations we've covered in the past. We've had several that have had angular velocities. But think about this one where we did a tangential velocity was equal to angular velocity times radius. And that is actually what we're going to do. This is tangential. This means linear velocity. That's the same as over here. We just went to the extra step of putting that t in there to signify that this was was not rotational velocity back when we covered it. So what I could do is I could rearrange this equation for omega, which would be pretty easy to do. And then I can substitute this right here, that guy, in for omega right there. And so that's actually what I'm going to do next. So let me do that equation work. So we're just kind of using these equations to our advantage. We got r squared. And then this is getting placed in here. So we're going to have vt over r. And that part all is squared. And so I'm going to rewrite this again. And I'm going to square those. There we go. Kind of a lot of equation work. Okay, that looks all right. And so now by doing that, hopefully you can see we've got r squared on the bottom and we've got r squared right there, which is terrific because that cancels out one of those variables that we did not know. And so now I'm going to rewrite this. I'm now going to drop that t. We knew this was a linear velocity or a tangential velocity, whichever way we wanted to say it. And it was kind of important to write over here so that we were kind of telling the difference between these two. But now it makes more sense to drop it so that we can more easily see that we have like terms here. If you notice here, we've got 1/2 v squared, and then here we have 1/2 v squared, which is perfect. We can now combine these, and we're going to end up with gh equals just v squared. We're going to have 1 v squared once we add those two together. This wants to know the velocity at the bottom, and we're now in a position where we can solve this thing by rearranging to that. So this thing boiled down to the square root of gh, which is pretty amazing to get something equation-wise that ends up being quite complex here. And by the time we get down here, the only thing that we need from the problem is the height, because we know the g. So at this point, we're just going to plug in, and we got our 9.8, and we had our height of 3.0, and we can solve that out and get our velocity at the bottom of this slope. So I'll let you guys do that from there. Hopefully that video helped out.